Hey there, physics. So this next unit here is about what's called circular motion. Circular motion, kind of obviously, motion in a circular path, right? A little bit different from the kind of motion we've talked about up until this point. Up until this point, we've talked about, objects moving in a line or in a curved path like a projectile. But this is circular motion where you go all the way around in a circle and come back to where you began. So at the beginning of the unit here, we're going to talk about things like, like Ferris wheels and cars on a racetrack, or maybe, spinning something on a string over your head. Later on in the unit, we'll go on and we'll talk about other kinds of circular motion, or nearly circular motion. We'll talk about what's called celestial mechanics, the motion of the planets, the orbits of the planets, asteroids, comets, those sorts of things. For our first lesson here today, to introduce circular motion, we want to be able to find the centripetal acceleration and the centripetal force on an object in circular motion. So let's go ahead and let's talk about some of the basics of circular motion. Okay, so here you should be able to see kind of a little picture of an object in circular motion. You can see there's two dots there, right? And there's a red dot and there's a blue dot, and the blue dot is moving in a circular path around the red dot. So for objects in circular motion, oftentimes we will talk about kind of the center point of their circular motion, and the center of that circle we often call the axis of rotation. So as we talk about circular motion, that's an important word to understand, is the axis of rotation is the center point of the circle, right? We also need to talk about some other terms a little bit differently than we usually do. Think about for a minute this object that's in circular motion, okay? It starts off at a certain point, and it goes around, and it comes back to the point at which it began. So if we were to try to calculate its velocity, the same way that we've been looking at the velocity of other objects up to this point, what would happen? Okay. Well, if you recall, velocity is delta x divided by delta t. But think about the delta x. If it goes around in a circle and comes right back to where it began, then delta x is 0. So no matter how long it takes to go around that circle, we would calculate its velocity to be 0. Okay. So usually we talk about velocity for objects in circular motion a little bit differently. Usually instead of talking about their velocity, we'll talk about what's called their tangential velocity. Okay. The tangential velocity is the velocity in a direction tangent to the circular path of its motion, or at a right angle to the radius of the circle, right? Tangential velocity will usually use a variable v with a subscript t, so vt is tangential velocity, and then just like velocity, it's measured in meters per second. The tangential velocity you can think about is think if I had an object on a string and I were twirling it around above my head and I let the string go, what would happen to the object? Would it keep moving in a circular path? No, it wouldn't. It would fly off in a direction tangent to where it was at that particular moment, with the velocity that it was moving at that moment. So the tangential velocity you can kind of think of as what speed would it, or what velocity would it fly off at if you suddenly released it from its circular motion, right? That's your tangential velocity. Okay. An object's tangential velocity, it depends on a couple of things. Okay, here's another diagram here, and in this diagram you can kind of look at these two objects. There's an object A and an object B, and they're both in circular motion around the same axis of rotation, but you can see they're at different distances from that axis of rotation. Now let me ask you, if both of these objects moved around in their circular paths in the same amount of time, what could you say about their velocities? Well, you could see that object B would have to move around faster in order to make the complete circle in the same amount of time, because object B has a longer path to take than object A. The circle for object B is bigger than the circle for object A, so it would have to travel more distance in the same time. So if they both made their circles in the same time, object B would have to be traveling faster, right? And so what's the difference between object A and object B? The radius of the circular path for object B is larger. And so the object's tangential velocity, you can tell, depends on the radius of its circular path. Okay, one other thing to notice about objects in circular motion here is that they are constantly changing direction. Okay, with a constantly changing direction, this object is constantly accelerating. You can't have circular motion without acceleration, because to change direction, that's an acceleration. So these objects that are in circular motion constantly have an acceleration. And that acceleration for an object in circular motion, we call the centripetal acceleration. Okay, the centripetal acceleration is kind of an acceleration that always points towards the axis of rotation. So if you think of it, you can look at the diagram that we have here. You can see the tangential velocity off at the side, but you can also see the centripetal acceleration pointing towards the center. So where that object is, the centripetal acceleration points towards the center. And as the object moves around the circle, when it comes around to the other side, that centripetal acceleration will be pointing the other direction. Right, so the direction of the acceleration is constantly changing, and the direction of the object's motion is also constantly changing. Okay, this centripetal acceleration, we call it centripetal acceleration. It's the acceleration involved in the circular motion there. We use a with a little subscript c to talk about centripetal acceleration, and then it'll be measured in meters per second squared, just like you're used to measuring accelerations. Okay. Now, we can calculate an object's centripetal acceleration fairly easily. Centripetal acceleration is equal to the tangential velocity squared divided by the radius of the circular path. So we can know the centripetal acceleration by taking vt squared divided by r. Pretty simple. Let's take a look at an example of how to use this equation. Let's have a look at an example of a problem you might see using this. It says a test car moves at a constant speed around the circular track. The car is 48.2 meters from the track's center and has a centripetal acceleration of 8.05 meters per second squared. What's the car's tangential velocity? Okay. Well, let's take a look at what they told us. They told us the car was 48.2 meters from the center. That would be my r, my radius. 48.2 meters from the center. They also told me the centripetal acceleration was 8.05 meters per second squared. So AC and the question asked me to find the tangential velocity. Okay, so let's go ahead and solve this problem here. So we'll take these numbers and we'll put them into the equation. AC, I know is this much. We don't know VT, so we'll leave here VT, and don't forget that that's squared. And then R we know is this much. Okay, so let me get my calculator, and we will multiply this 48.2 to the other side of the equation. .05 times 48.2, three significant figures. I'm going to round that to 388, and that's VT squared. So, to solve the equation, I'm going to take the square root of both sides. So VT would equal to about 20 there. And I need 3 significant figures. So here I got 19.7. And for velocity, that'll be meters per second. So not too tricky to use that equation there. Okay, another thing to keep in mind about objects in circular motion is that in order to maintain their circular motion, there has to be a force. Okay, all objects in circular motion are experiencing a force to hold them in circular motion. If you recall, the second law of motion, so that the force is equal to the mass times the acceleration, right? Well, the acceleration that we're talking about in circular motion is this centripetal acceleration. So let me replace that with this term right here. So we'll call that Vt squared over r. So the force, what we call in circular motion, we call it the centripetal force. The centripetal force, we say F with the little subscript c, and of course it's measured in newtons. So here we have another equation. The centripetal force is equal to the mass of the object times the tangential velocity squared divided by the radius of the circular path. And you can put the mass up here in the numerator with the rest of those. Let's take a look at a problem involving the centripetal force. Okay, the problem says a pilot is flying a small plane at 56.6 meters per second in a circular path with a radius of 188.5 meters. The centripetal force needed to maintain the pilot's circular motion is 1.89 times 10 to the 4th newtons. What is the plane's mass? Okay, well, we can use our equation here to solve that problem. Let's determine what each thing is here. So it says that it was flying at 56.6 meters per second. That would be the tangential velocity. It says that the radius of its circular path was 188.5 meters. And it says that the centripetal force is 1.89 times 10 to the 4th. 1.89 times 10 to the 4th newtons. And the question asked me to find the mass, so M. Okay, so let's go ahead, we'll put the numbers in the equation and we'll work this out and see what we get. So let's see, I'm going to do my work over here. So FC is this much, 1.89 times 10 to the 4th. In the numerator up here, we have the mass, which I don't know. So I'll put M times Vt squared. So here's Vt. So 56.6, and don't forget that that is squared. And in the denominator, we have the radius, which is 188.5. Okay. So let's go ahead and solve this. I'm going to grab my calculator. I'm going to multiply the 188.5 to the other side of the equation. So let's see, that was 1.89 times 10 to the 4th times 188.5. And I'm going to want to keep 3 significant figures here. So 3.56 times 10 to the 1, 2, 3, 4, 5, 6th power. Which makes sense because 4 and 2 would be 10 to the 6th. Okay. Over here, I'm gonna square this number. So 56.6 squared. 3 significant figures. I get 3,203. So let me write that in scientific notation. 3.20 times 10 to the 3rd times m. And then to solve for m, we'll divide both sides by that number right there. So 3.56 times 10 to the 6th divided by 3.20 times 10 to the 3rd. And I get syntax error. Let me see, where did did I mess that up? Oh, I missed the 6. There we go. And I get 1,112. We need 3 significant figures there. So let's say that's 1,110. And a mass is in kilograms. 3 significant figures. If you prefer, 1.11 times 10 to the 3rd kilograms. Okay, so not too difficult there. We will have a lot of problems in this unit involving scientific notation. Here we had an airplane, that was traveling with a large enough force that we needed to use scientific notation later on when we're talking about planets moving millions or billions of kilometers and weighing many thousands of kilograms, much more than thousands of kilograms, huge numbers of kilograms. We will, of course, be using a lot of scientific notation with those kinds of things. So, yeah, but you can see that what we're doing here, not that tough. Okay, so there was a little bit about the centripetal acceleration and the centripetal force, and hopefully that helps us be able to find the centripetal acceleration and the centripetal force on an object that's in circular motion. So until next time, take it easy.